Hello, everyone. Welcome to today's Quantum Spacetime seminar. The first speaker for the year is Igor Klebanov from Institute for Advanced Studies in Princeton University. He'll be talking to us about ON SP2M and OSP12M models. Over to you, Igor.
Thank you very much for the invitation and Happy New Year, everyone. Yeah, it's nice to begin the year. Let's hope it's better than the previous one. But although it seems to be off to a somewhat turbulent start. Okay, I see a chat. Yeah, thank you. All right, so I'll talk about this sort of line of work I've been doing on theories with cubic interactions, which started almost 8 years ago already on ON models. And then back in 2015, we wrote a not so well-known paper on OSP12 model. And somehow recently I came back to that, prompted by a question from some colleagues. And so my last paper is on these OSP12M models. And another thing is actually this year is the 50th anniversary of epsilon expansion of the Wilson-Fisher paper. So you'll see there will be lots of epsilon expansions. And actually, very sadly, I learned that Michael Fisher died in November. So it's a kind of tribute to him. So here is a list of a few papers that my talk will be based on, but of course, also on some more classic results. Okay, so let me just start with something all of you know, which is the ON model. It's a textbook example of quantum field theory and statistical field theory. And for example, even in Peskin and Schroeder, you can find a lot of results. It all starts with just a theory on a lattice with some ON spins. For example, some n-component vector whose length is 1. And then you tune it to some critical temperature. And there it's described by the continuum field theory with no mass. So at the phase transition, the mass squared term is tuned to 0. And then that's how we study these second order phase transitions using field theory. And in particular for n=1, it's the famous Ising model. So this 5-4 theory, if you study it in 3 and 2 dimensions, it gives in principle operator scaling dimensions of d=2 and d=3 Ising model. But in general, this is a strongly coupled theory, so we need some clever tricks for studying it. So one of them is Wilson-Fisher 4- epsilon expansion, which actually was introduced right around 50 years ago. Then there is the 2+ epsilon expansion in the ON nonlinear sigma model. But if you don't like going to continuous dimension, you can even do 1/n expansion directly in d=3. Although it's not as good for low n as these other expansions. And lately, of course, there is a lot of focus on these models because of the numerical conformal bootstrap, which allowed to test various conjectures and get more precise estimates of critical exponents. So as I mentioned, the golden jubilee of the epsilon expansion, here is the beginning of the Wilson-Fisher paper. I think it's the first time you could see d=4 - epsilon in print. And this was published January 24, 1972. So we should all be celebrating now. And you'll see a lot of epsilons actually in my talk. Okay, so let's talk about 4 - epsilon expansion in this ON symmetric quartic field theory. The one loop beta function is well known. There is -epsilon lambda term. This epsilon arises from the fact that the coupling has some, it's slightly irrelevant to the fourth term. And then there is this term comes from the 4-dimensional positive beta function for this theory. And this, of course, has the weakly coupled infrared stable fixed point at lambda star, which is of order epsilon. And there is also 1/n here. So the epsilon expansions of the scaling dimension, well, the leading classical term for the free field is just d/2 - 1. And then there is the anomalous dimension, which for the phi field is of order lambda squared. So this term here comes from the anomalous dimension, and this is just the dimension in free field theory. And then similarly for the phi squared, the mass operator, there is d-2 plus gamma phi squared. And you see that this is, here the correction is actually of order epsilon rather than epsilon squared. So this has been just an amazing tool. And now the results are available up to 6th order in epsilon through the amazing 6-loop beta functions and 6-loop anomalous dimensions. I think this paper by Kompaniec and Panzer from 2017 has a lot of these results. And who knows, now maybe people are on track to even 7 loops. And this allows, so this is a whole industry. You can develop this series and then do Padé approximates to resum them, because of course the coefficients begin to become big. So you cannot simply plug in epsilon equal 1. Actually, for the Ising model, it's well known that just plugging in epsilon equal 1 gives a very small correction here, but this is not always the case. Okay, so now, so this is all well and good below 4 dimensions, and everyone knows that the upper critical dimension of these magnets is 4, right? But I'll talk a little bit about what happens above 4 dimensions. So you can say, what's the deal? Like, how can you go above 4 dimensions? And it turns out that above 4 dimensions, something totally different happens. Namely, you have to go to the negative quartic coupling. So for lambda less than 0, the d=4 model is actually formally asymptotically free. And there was this very impressive work by Szymanczyk in 1972-73. He was one of the first people to search for asymptotically free theories, and he wrote a paper in December of 1972, which pointed out that the UV asymptotics of this negative coupling theory are safe. You can really, they're computable. And then right around that time, people also realized that if you formally go to 4 plus epsilon dimensions, then there is a UV fixed point at negative coupling. So this is, so basically if you just take epsilon to be negative, then this lambda star also becomes negative. And you can say this is sort of very strange, right, to be talking about a theory with a negative coupling constant. But it's actually not totally unstable. I think what happens is it's actually kind of metastable. And from the point of view of the calculation of scaling dimensions in this theory, what happens is that you get very small imaginary parts due to the instanton effects. Basically, people realize that the instant, so in this theory with negative lambda, there are instantons. And this was pointed out, I think, by Lipatov originally, or many people in the 70s. And then it became clear that these instanton effects provide the scaling dimensions with these exponentially small imaginary parts, like e to the minus n over epsilon, actually. And one of the people working on this was Alan McCain. So they did some calculations for the 5-4 theory in the late 70s, but for the ON model in 1984. And you may recognize 1984 as the date when lots of people gave up working on quantum field theory and moved over to string theory. So actually it's fun to read some of these very nice papers, and in some sense they weren't followed up on that much. So there is actually, so I will describe a little bit like what we did to follow up on this result. I mean, one big confusion about this theory, quartic theory above 4 dimensions, is that it's not renormalizable, right? While the theory in D less than 4 is super normalizable for even in 4 plus epsilon dimensions, it's not renormalizable, but you can formally find this UV fixed point and do some calculations there. But I will present like another formulation of the ON model, which is actually super normalizable.
Hi, Igor. At large n, you can presumably compute the quantum effective action of this theory, as a function of the field, sort of exactly.
Right.
And that I suppose that does go off to negative infinity at phi equals infinity.
I believe it does, but around the sigma equals 0, I think it does have positive curvature.
Okay, thank you.
Yeah, and that sort of makes it metastable. This is actually what we did in a paper 2 years ago, which I'll mention a little bit. So in fact, this effective action using the Hubbard-Stratonovich field is my next topic. So if you, for example, like going back to so another motivation and how I got into these ON models was because they have something to do with higher spin theories in ADS space, right? So, for example, the T equals 3 ON model in the UV, it's just the free theory, but in the IR, it's the interacting theory where the phi squared operator has dimension 2 plus order 1 over n. So there is a large anomalous dimension for this phi squared field. And in ADS4, the free theory is described by this Vasiliev higher spin theory. And it turns out that the interacting one just corresponds to taking a different boundary condition corresponding to Dirichlet rather than Neumann. So this is just an aside for another motivation to think about its ON model. So now the 1 over n expansion of the CFT was studied a lot, actually starting the early 70s with the work of Wilson and others. And one introduces this Hubbard-Stratonovich auxiliary field, which couples to phi squared operator. And then, so in the infrared, this term can be ignored, and then you can develop, it's a kind of resummation of the series. So if you write down this effective action for the sigma field, at large n, all that's enough is to exponentiate the 2-point function of the phi squared operator. And then you get the induced dynamics for this auxiliary field sigma, which endows it with effective propagator, which goes like this. It's just a Fourier transform of this computation. And this corresponds to the 2-point function of sigma field falling off like 1 over x minus y to the 4th power with some coefficient, which is a function of d. Right, and this is just the familiar fact that this phi squared operator to leading order in n just has dimension 2, right? And this is what I was saying here, that it has dimension 2 plus some 1 over n. But people have gone beyond this leading order and computed 1 over n corrections. There are a lot of classic papers from the 70s and 80s on this. So for example, the 1 over n correction to the dimension of the phi field itself. So again, there is this free field, and then there is plus 1 over n times some function of d plus 1 over n squared, another function. And it's certainly known up to order 1 over n cubed, which was computed by another physicist named Vasiliev, who died long ago. but not Misha Vasilyev, but he and his group worked on these corrections a lot. So there is a trick to sort of compute this, this correction. It's just basically a diagram where you attach, it's like a self-energy diagram where you attach a sigma propagator to that of the phi field. After regulating it a bit, you find the expression for eta 1, which I think has been known for many, many years. I think almost 50 years, probably. And it's interesting to plot this expression as a function of d. So if you plot it, of course, it's positive between 2 and 4. And this is just a sign of the unitarity of the large N theory, because once it goes negative, then you see that the leading 1/n correction will violate the unitarity bound. So it's totally expected that between 2 and 4 dimensions this does not happen. But a somewhat less appreciated fact that this is also not the case between 4 and 6 dimensions. Basically, it hits 0 at 4, but then starts going back up again, and only for d above 6 does it go negative, right? And this was actually, and the same is true for this coefficient C sigma of the 2-point function. So it seems like the large N theory, at least perturbatively, has some nice unitarity properties, even above 4 dimensions. And this was actually noticed in the mid-70s. In particular, Parisi pointed out that this range between 4 and 6 dimensions may be nice for the definition of the theory.
Igor, one question.
Yes.
So, I mean, isn't it true that at non-integer dimensions, the theory is not quite unitary because of these other operators?
Yeah, there are much higher dimension operators. Yeah, that was emphasized by Slava Rychkov and others.
Right.
But that happens with some high dimension operators.
Okay. But a priori,
also, I'm not totally sure about the large N, whether this problem persists at large N. Yeah, this is just the dimension of the phi operator, and that, at least formally, looks unitary. I will actually tell you that, I mean, this theory is not completely unitary, but it can be made extremely close to being unitary.
But when you say that, you also, this is a statement about the full spectrum, or?
Well, you can already see a problem for this leading phi operator. Basically,
okay,
the scaling dimension acquires a small imaginary part, even here. Like naively, it seems just positive, but but it's of order e to the minus n.
But is there any a priori expectation or significance to the positivity of this, only the positivity of this anomalous dimension?
Yeah, I think what I believe to all orders in 1/n expansion, the theory may be unitary.
Oh, okay.
Yeah, that's at least what, based on this evidence.
Okay. Thank you.
Yeah. So then and also the violation of unitarity is a bit different from just real dimensions going below unitarity bound. It's more like, I'm not sure what's a good name for such CFTs which acquire a small imaginary part. Like some people call them complex CFTs, but here the way in which they acquire the imaginary part is rather different. So I don't know, maybe one can call them metastable CFT or something like that.
Thank you.
No, thanks. Yeah, please interrupt me, because yeah, I definitely would like to hear your comments. Yeah, so this special range between 4 and 6 was already pointed out in a very nice paper by Parisi around 1975. And this I already said, that the UV fixed point, even in epsilon dimension, occurs at negative coupling, so you could suspect this theory is somewhat nonsensical. Actually, when Semantic was working on this negative coupling pi-4 theory, he was criticized by various people that there is no ground state. But it's not totally clear. He kept hoping that this is not a fatal problem. And I think in some sense he was right. That it could be that, I don't know. I'll show you a few more facts about this theory. But the main thing that we did actually with Simone Giombi and Lin Fei back in 2013 was to point out that between 4 and 6 dimensions, there is another ON symmetric field theory where you add one more field. So instead of the quartic theory, which is non-renormalizable, there is a cubic theory, which is renormalizable. And it has two coupling constants, G1 for sigma phi I coupling and G2 for sigma Q. So by adding this extra field, you make the theory both ON symmetric and perturbatively renormalized below 6 dimensions. So we started studying this theory, and we found that indeed something happens, something nice starts happening at very large n. So what do you need to do? You basically just compute the 2 beta functions, which is a standard field theory exercise. And you find that for large n, there is IR stable fixed point where both couplings are real, both G1 and G2 are real, and they're given this expression. So here is a plot of what happens, but it turns out that that this is only true when n is bigger than 1040, which is a very large number. Once n goes below 1040, then these what happens is that 2 fixed points just merge and go off to a complex plane. So just perturbatively, you lose these real fixed points.
Sorry,
but for n equal 2000, for example, you see this plot, and indeed you can float to these IR fixed points. These two are just physically equivalent because they correspond to changing I to minus. So and this is what happens when n is smaller. This point of intersection in real G's disappears. You no longer have even perturbatively.
Igor, on your previous slide, you had an epsilon. Was that a 6 was the dimension written as 6?
This is all in 6 minus epsilon.
Minus epsilon.
Yeah, this is all. This is just the leading 6 minus epsilon calculation, right? Then the epsilon gets removed by this transformation, right? So it all happens at very weak coupling.
So can I think of it this way? Can I think of this new way of looking at this theory this way? That in 6 dimensions, the phi cube operator becomes marginal.
Yeah. That's the upper critical dimension.
So this is like perturbing the theory by adding like a phi cube. And going down. Okay. And are you going to say that these two theories that you've talked about are actually the same theory?
Yeah, exactly. So one of them is this is the UV completion. That's what we want to say. That this formulation is actually the UV completion of the quartic theory, which is not renormalized. And
the fact that it's phi cube also indicates that it's likely to be unstable if you compute a quantum effective action.
Right. So but if we just work at the level of perturbing in 1 over n, you can, for example, try to check whether the scaling dimensions of order 1 over n are the same as you get from the original model. Right. For example, you can take these formula here, which apply to the original model, and expand them in 6 minus epsilon dimension. Right, because this is known, so you get the term which is 1 over n times a series in epsilon. right? And 1 over n squared times the series in epsilon. And compare them with what this model gives, and it always agrees. I mean, you can kind of see why you need this, in some sense, this extra free field sigma. What happens is that this sigma field that you get in Hubbard-Stratonovich, it just starts acting like a free field in 6 dimensions, just a canonical Gaussian field. Why? Because you see that it always has dimension 2, but in 6 dimensions, dimension 2 is the free dimension. So very near 6 dimensions, it just acts like an extra dynamical field. And this is a pretty common phenomenon. It was actually known for the Gross-Neveu model. And probably some of you heard about this Gross-Neveu-Yukawa model. We actually didn't know when we originally worked on this, but then we realized that this was applied to this fermionic model. So all of this is pretty solid in perturbation theory. So in particular, we see that, for example, this scaling dimensions at the IR fixed point agree with this, all the results that you can develop using perturbation theory, or 1 over n perturbation theory. But
sorry,
now,
Igor, just to understand, I mean, in the 6 minus epsilon dimensions, this is an IR fixed point, right? Or or UV?
IR, just conventional IR fixed point.
I see.
Because in 6 minus epsilon dimension, the phi cube is just a slightly relevant operator.
Okay.
So you can basically say that actually everywhere below 6 dimensions, this is a super normalizable theory.
I see. And
with a caveat that it's unstable.
And in 4 plus epsilon dimensions, this would be the UV fixed point?
No, this theory, even in 4 plus epsilon, would have an IR fixed point. It's just strongly coupled.
Okay. No, I mean the other.
This theory is only weakly coupled slightly below 6 dimensions, because the G's are small, suppressed by epsilon. But you can, for example, you can imagine just on a computer studying this theory in D equal phi.
Okay.
And just numerically studying it, it's strongly coupled there. I mean, our original aim is to find something interesting in equal phi.
Mm-hmm. So, but the phi to the
if not for this sigma cube instability, it would be fine.
But the phi to the 4 theory in 4, the one that we usually study in 4 minus epsilon dimension, if we did that for 4 plus epsilon dimensions, that would naturally.
In 4 plus epsilon, it's just formally defined, but it's again is unstable because lambda is negative there. So there is a kind of whole different regime for this ON model between 4 and 6, where the theory is not quite stable.
Okay.
And it can be either described using large N method or using this theory.
So is it right? So is one way of saying this that if you start from the free theory between 4 and 6 dimensions, you start from the free theory, and there's an RG flow triggered by the phi cube operator that can be made to go to this new theory, and then there's another RG flow.
I think this in some sense is I would say this is the right definition of the theory at large but finite n.
Right.
You can either formally expand in 1 over n, as people were doing in the 70s, or you can work at large but finite n using this theory, which is renormalizable.
Okay. Right.
I think this was actually not done back in the 70s. I mean, this is one new thing I think we did. What was done back in the 70s is to do this 4 plus epsilon expansion for the quartic theory, which is slightly non-normalizable.
Right.
And our results actually agree with that. Where we can compare, they agree with that.
Right. So sorry. So there'd be an RG flow from the free theory to this theory, triggered by, roughly speaking, the phi cube operator, and then a second RG flow from this theory down to the
Quartic theory. Yeah.
yeah, triggered
By
by
adding the
Markov.
sigma squared operator.
Yeah.
Yeah.
Okay. Thanks. Yeah.
Right. Right.
Also, there is a story in, I mean, there's this fixed point in 6+ dimension, right? If I remember correctly, isn't that, maybe I'm not remembering correctly.
There is a fixed point. So let me just mention one thing. So actually the pure cubic theory for n equals 0.
Yeah.
Michael Fisher in 1978 pointed out that in 6 minus epsilon dimension, it has a fixed point at imaginary coupling. It's renormalizable, and I'll come back to that. And this is actually a very good thing. It's a very good theory, and it describes a non-unitary Li-Yang. It describes a family of non-unitary theories, which in D equal 2 continues to the famous Li-Yang TFT.
No, maybe it is the same one, but I was just having in mind just the phi cube theory in 6 dimensions.
Yeah, we're in 6 plus epsilon, right?
6 plus epsilon, yeah. So
yeah, I think, yeah, if you read Semantics paper, some Mac, I think, pointed out he was looking at this 6 plus epsilon theory with real coupling, but it's not clear what this theory means, again, because it's not renormalizable. You again, I mean, you can go to sort of like try to do something in 8 minus epsilon again to make that theory better.
I see.
And this actually, there is a family of theories like in 8 minus epsilon, 10 minus epsilon.
I see. Thank you.
So then I'll come back to this imaginary coupling story, but for now, let me just make a few more comments about this this theory with n bigger than 1039, where there are real fixed points. So we, encouraged by this, we then with Fay, Jomby, and Tarnopolsky, we did a 3-loop calculation and tested out some of this agreement with 1 over n, and it continued to work. So this was in 2014, and since then, Gracie did the 4-loop, and now Kompaniets and Pikilner in Russia did 5-loop, and Gracie. And so this is all kind of progressing, and I think it continues to work. So again, you can, for example, if you develop this 1 over n expansion of various observables, you can essentially compare the 1 over n coefficient with the function that I showed before, like 1 over n times epsilon minus 11 over 12 epsilon squared minus, and so on. And this agrees with this function that I showed before. So this double expansion is a good thing, which agrees with what with this 1 over n result, which was known long ago. So this is just a sanity check that this theory does make sense in the 1 over n. But then there is a question that immediately occurs, and you raised it, that what about the sigma cube instability? Well, I mean, if you sort of work on a cylinder, right, R cross SD minus 1, the conformal coupling of scalar field actually renders the perturbative vacuum metastable rather than completely unstable. And there are some instantons. So we wrote a paper in 2019 with Jomby, an undergraduate, Huang, Hufu, and Napolsky, where we studied this this function, which gives the imaginary part. And actually, in 4 plus epsilon, this function agrees with what was known to McCain et al. Back in 1984. But there you get e to the minus n over 3 epsilon, and here you get, this function is actually just the free energy of a conformal scalar in d minus 2 dimensions. So this is a cute result of this paper. But we basically see how the instanton works in continuous dimension between 4 and 6. And this helps us say something about 5 dimensions, which is not near 4 and not near 6, right? And so what happens in 5 dimensions, so this f is a small number. It's like 0.0638, which is just the 3-sphere free energy. And this is the plot of this function. You see it blows up as 1 over epsilon near 4 and near 6. And it's pretty small near 5. But if you crank up n to around 500, e to the minus nf is only like 10 to the minus 14, which is really below the numerical accuracy. And people actually looked for ON models in 5 dimensions and did find nice islands. And within these islands, there seemed to be good agreement with the 1 over n expansion. So what could be going on is that if the imaginary part is so small that it's unobservable, you can make it arbitrarily small by cranking up, and it just goes down exponentially. So already around 500, there seems to be some kind of near critical 5-dimensional model. And people, you can indeed sort of discover it using numerical bootstrap. I guess the question in my mind is, can you somehow see it without? The unfortunate thing is that n is so large, so it's very hard to simulate the, ON magnet with n equal 500, but it's still an amusing thing that this model seems to exist in 5 dimensions with really incredibly small imaginary parts. So in that sense, even though the instability of the potential is a concern, it's sort of, in some sense, it gets defeated by large n. Does this sound crazy? Or?
It sounds great to me. I mean, it sounds to me like the statement that the full potential has an n outside it. So if there is a local minimum,
right.
You're going to find it hard to see that the potential goes down later at large n.
Yeah. As we know, large n is a great stabilizer, right? So like we always worked with these matrix models where the potential is really unstable, but large n stabilizes it. Something similar goes on here. But I think this is the best evidence for some kind of almost unitary CFT in 5 dimensions so far. Of course, most people would say it's not unitary because technically there is this imaginary part. I mean, without supersymmetry. I mean, there are, of course, super formal theories. Okay, so this is pretty much what I had to say about the ON, which was the first part of my talk. And now let me switch gears and sort of do something closer to what Michael Fisher was doing, which is go to the region of pure imaginary fixed point. And there is no concern. Yes.
Could I interrupt? Sorry, I'm getting confused about one thing. If I look at the RG flows, there's an RG flow from the free theory to this new theory between 4 and 6 dimensions. And then there's also an RG flow from this new theory back to the free theory. Right? That's what the 4 plus epsilon dimension expansion tells you. But so I'm getting confused. I mean, is it? I'm wondering how this matches the C theorem, and is it that we even approximately? And is
I would say that the critical point in 4 plus epsilon dimension interacting critical point is just a continuation of the critical point you see in 6 minus epsilon dimension.
Good. But we know from the 4 plus epsilon point of view that this new theory that you create in 4 plus epsilon dimensions has a relevant operator which allows you to flow to the free theory, right? Namely the 5 to the 4 operator.
Right. The phi squared.
No, I was thinking the 5 to the 4. I mean, in the usual dimension, 4 minus epsilon, 5 to the 4 is the operator that allows you to go from free to Wilson-Fisher.
Yeah, I think phi squared is an irrelevant operator.
Is irrelevant even around this new fixed point? It's irrelevant around...
Yeah, I think so.
Well, it's irrelevant around the free theory in 4 plus epsilon dimensions, right? So I think it must be relevant around this new fixed point.
Well, if you just go to the large n, right? So you know what the large n dimension of this sigma is. Yeah, I think it's say 2 plus 40 epsilon over n. So you just have to take twice that, and it's basically irrelevant.
But is it sufficient to take twice that, because the 1 over n corrections could change, right?
Yeah. But I mean, we did worry about this, and I think, we did have checks of this C theorem or F theorem. Using these.
But I was wondering, sorry to keep on, but I was wondering whether the resolution might be that you start with a theory of n plus 1 free scalars and then eventually flow to a theory of n free scalars. And that's how the C theorem would be preserved.
Yeah, that's related to the resolution. Yeah.
Okay, yeah, thank you. Then I understand.
Yeah, I think that is related to that.
Okay, thank you.
Yeah, certainly. If you just add the sigma squared term, right, then you generate this phi squared.
Yes.
Yeah, definitely this extra free field near 6 dimensions played a role in.
Okay, yes, I think I understand. Thank you.
So the idea is that that you start from an n plus 1 free theory of n plus 1 scalars, then flow to this theory, and then in turn flow to the theory of n free scalars.
Right.
In one of these intermediate 4 to 6 dimensions. One could of this flow in those steps, right?
Right. But I think there is only one sort of interacting fixed point with ON symmetry for any D. That's what I'm trying to say.
And also this would mean that the central charge would have to be kind of, I mean, this in between the two, right?
Yeah. That we did check.
I see. Okay. Thanks.
Yeah, it's basically the new point of view on what, because people were always somewhat dissatisfied by this 4 plus epsilon expansion. It's always a little funny because the theory is non-renormalizable. But the 6 minus epsilon expansion of this cubic theory, it's perfectly sort of palatable modulo what happened at large field.
Yeah.
Okay, so let me talk a little bit about this another set of theories where we can take this theory and replace the n commuting scalars by say 2m anti-commuting scalars. So it's a theory of 2m anti-commuting scalars and 1 sigma scalar, and it again has 2 coupling constants. So that we did in 2015. And then you can just actually obtain the beta function in 6 minus epsilon dimensions by changing n to minus 2m. Like you basically send n to minus n. That's a standard trick going between commuting and anti-commuting scalars. And now we actually find our stable fixed point at imaginary values of the coupling constant. I mean, one simple way to see why they become imaginary is if you go to the expression for the coupling constants, there is a square root n, right? So if they're real for n, they will be imaginary when you replace n by minus n. And actually having imaginary coupling constants that completely removes the worry about the instability of the sigma cube, right? Because now the path integral just oscillates at large field. It just oscillates rapidly, and there is no issue with non-perturbative instability. So the path integral is well defined and may describe some critical but non-unitary statistical system. And this is known, for example, for this Michael Fisher's pure phi cube theory. But now we notice something very amusing when, for the special case when M is just one, namely we take only one pair, like theta, theta bar, and sigma. In this case, there is a relation between these two G's, where it's a very simple relation that G2 is equal to twice G1, and both are pure imaginary. And then there is a symmetry enhancement to OSP1, 2. It's easy to see because with this combination of couplings, you can write the interaction as sigma squared plus 2 theta, theta bar to the 3/2 power. And the expansion in theta, theta bar just terminates at the linear term because theta, theta bar squared is just 0. And you just pick up these two terms here with exactly the right ratio. So you can view this theory as just really a theory with one coupling constant and this extra symmetry.
So theta is anti-commuting while sigma is commuting.
Theta is anti-commuting. It's just one pair of anti-commuting variables,
sigma
is still commuting.
And so is roughly the both. I mean, is it roughly that theta behaves like a fermion and sigma behaves like a boson under the
right. So yeah, any loop of theta gives a minus sign. That's why you change n to minus n.
Thank you.
So then we found these. So if you define G1 as Ix and G2 as Iy, you then see like IR stable fixed point in this theory. And due to this OSP1-2 symmetry, that's how we notice this, that the scaling dimension of sigma and theta are identically equal. They're just part of this OSP multiple. This is only true when M is 1, but it's not. For example, if you play the same game and take theta 1 bar, and theta 2 bar, it just doesn't happen. So just for M equal 1, this special enhancement happened. And so then, in fact, people have been working on these OSP1-2 models for quite a while, and they're of much interest to rigorous statistical mechanics people. And they realize that there are these sigma models, supergroup sigma models in 2 plus epsilon dimensions, or in 2 dimensions, which were discovered around 2004. And recently it was clarified by Bauer, Schmidt, and collaborators. Basically, you take this action and plug in a constraint, that this OSP1-2 invariant constraint, but you only pick one solution rather than the other. And then you can think of this as sigma model with this fermionic hyperbolic space. So you can think of this as a kind of fermionic version of anti-de Sitter space, something like that. And then you get this model by just plugging in this sigma. And it's actually asymptotically free for negative G squared. So you can do 2 plus epsilon expansion for this model. Similarly to how, because negative coupling 5,4 is asymptotically free, you can do 4 plus epsilon expansion. But what people actually did not know is that, again, there is a UV completion, which is this cubic model. So this sigma model is non-renormalizable as soon as you go to above 2 dimensions. But then this other formulation looks better, and now it's completely stable. There's no complaints about it. So one can then do this, what the trick that people sometimes do, that you can develop 6 minus epsilon expansion using this cubic model and match it to 2 plus epsilon expansion using the sigma model. and you get some Padé approximants, and they actually work extremely well because people know how to simulate this model rigorously on a lattice. And it turns out that the model described by the sigma model is the limit of Q state Potts model to Q equals 0. It's called the random forest, like random spanning forest. So I found some old paper on an old paper on these Monte Carlo simulations, and the agreement is very good. And also, like the story with the Potts model, it also goes back to the classics of statistical field theory. There was a paper by Zia and Wallace on n+1 state Potts model and its formulation in 6 minus epsilon dimension. So they invented this cubic Lagrangian, and then you can develop, for example, the calculation of scaling dimensions for any n. But now here is what the miracle is, that when you send n to -1, which is the 0 state Potts model, you find exactly the same 6 minus epsilon expansion as what this is. Like all the coefficients up to some high loop order are the same. So somehow it's a more like rigorous formulation of the 0 state Potts model okay, so now what about the Monte Carlo or like lattice formulation? Well, you can, by analogy with the spin model, you can basically, again, invent these OSP1 2M spins and just have the dot product for nearest neighbors. But the special thing here is that to evaluate the partition function, you only do Grassmann integral because sigma gets eliminated by the constraint. So everything is Grassmann integral, which is obviously much more rigorous than usual integrals. And people proved, these people, Caracciolo et al. Proved that it's equivalent to this random spanning forest. So here is a picture of a spanning forest on a lattice. Basically, it can have disconnected components, but it has to pass through every single lattice site. And they were simulated by these people, Deng, Garoni, and Sokol, in 3, 4, and 5 dimensions. And the results for critical exponents are in very good agreement with this, these numbers that I found by using 6 minus epsilon and 2 plus epsilon expansion. So in this case, it all seems like completely rigorous. There is no non-perturbative instability. And this cubic theory with imaginary coupling constants really defines some stable, well-defined path integral. Are there any questions about this?
What do the statistical mechanics people study this theory? I mean, is there a particular experimental application?
Yeah, it's a very simple model. It's basically you sum over spanning forests with some particular weight for each link. It turns out that it's really the limit of Q state Potts model to Q equals 0.
Okay. Thank you.
And this was apparently known to rigorous statistical mechanics people long ago. So what they noticed is that this model has something to do with this OSP1 2 sigma model, or this hyperbolic sigma model. So in fact, the reason I got really interested in it is at the Institute, I talked with Bauer-Schmidt, who wrote just recently a couple of papers, and he's very excited by this new understanding that you can think about this as a kind of hyperbolic space with the Grassmann continuation, this H02 space. yeah, this is this H02 version where you eliminate the sigma and you get this type of very simple Lagrangian. It's a lot like taking ON sigma model and continuing n to -1. But this is all done rigorously. So it's the O -1 universality.
Sorry, and one more question. Some time ago, Strominger and collaborators had looked at perhaps similar theories as possible duals to de Sitter space.
Exactly. That's actually why so the reason we started doing these SP2M models was inspired by this Aninas, Hartman, and Strominger paper. But they were working in 4-dimensional space and just taking quartic. I mean, they were primarily interested in D = 3, and they took the quartic SP2M model. There are some issues also about where it's asymptotic. Yeah, I mean, so in our paper, we discussed a little bit, but then we started sort of, just like how we went from the quartic to cubic model, we did the same thing for this. And I think we found something kind of potentially more interesting. I think that this whole issue of DS CFT for these models, I believe it's a little bit murky. There were some more detailed studies of the wave function of the universe, and I think they had some trouble with these interacting Grassmann.
I see, and the trouble was that the wave function turned out to be non-normalizable?
Yeah.
Okay, thank you.
Yeah, somehow, like people who study disordered systems, they like these anti-commuting scalars. I mean, it's a lot like Parisi-Surlas, right? And they took these quartic models and then wanted to continue them to D = 3 and think about this as definition of higher spin DS4. So in particular, Denef wrote some nice papers on that. I think they ran into some trouble indeed with the behavior of the wave function for these models. But there are some long papers by Denef and collaborators. But we kind of switched gears from speculative DS-CFT to rigorous statistical mechanics. Which, I mean, for example, these people, Bauer-Schmidt et al., they're really mathematicians, and they wrote some rigorous proofs of RG for this lattice model. And they actually seem interested in this cubic theory because they think that this cubic theory really gives a nice explanation for why the upper critical dimension is 6 and what happens below 6 dimensions and so on. Okay, so this, I'm already slightly over time, so let me just finish. So this was more or less what we knew back a few years ago. But then I started thinking about what about, say, OSP14, OSP16? We couldn't get these OSP enhancement from the cubic theory. And then I realized that you actually need higher powers than cubic. In particular, if you just take this combination sigma squared plus theta theta bar and raise it, say, to the power 5/2, then the expansion actually terminates because of the Grassmann property. It's sort of clear what happens, what goes wrong with this interaction if you say work with OSP14, because sigma squared plus theta 1 bar plus theta 2 bar to the 3/2 power is going to have a negative power of sigma because it doesn't terminate fast enough. And this doesn't make sense as a field theory. But if you raise it to the 5/2 power, then it makes sense. And this really works. So in fact, the most interesting new theory is the one with the quintic power, sigma to the 5 plus sigma cubed theta theta bar and so on. And I was able, so this quintic theory, its upper critical dimension is formally 10/3. But it's not crazy to develop 10/3 minus epsilon expansion. In fact, it was already done for pure quintic theory. And using some of these results, I was able to check that there is indeed OSP14 enhancement for this quintic theory, in that delta theta and delta sigma both have the same dimension as required by the OSP14. Actually, John Gracie, who is an expert on these loop calculations, he just for fun studied this quintic theory with ON symmetry. Then I just took his formula and set n to -4, and out pops this OSP14 enhancement. It was very nice to see. But now this theory in 3 dimensions is actually below the 10/3. So, and epsilon is quite small there. So you seem to get a model with very, very small anomalous dimension. It's an example of a very weakly coupled, but still not free theory. And in this case, no one has yet calculated 2 loop corrections, but I think it would be interesting. And also, there is a whole separate question of which statistical model does it map to for OSP14. It's something more complicated than this zero state Potts model. It's and apparently some mathematicians are working. I mean, the starting point is this OSP14 vector model and a lattice, but then you have to do these Grassmann integrals on each side and see what it maps in. Okay, so let me finish then. So first I talked about the UV completion of the sort of metastable theory between 4 and 6 dimensions with ON symmetry, which appears for sufficiently large n. The scaling dimensions have non-perturbatively small imaginary parts. And when they become ridiculously small, like, I don't know, 10 to the -20, you can sort of ignore them when you're doing numerical bootstrap. And it seems like people actually do see like they can't tell this from a normal CFT in 5 dimensions, that so far at least. So it would be actually interesting to clarify to what extent this works. But then there is a whole other set of theories which are stable but manifestly non-unitary, which have cubic interactions with coefficients that are pure imaginary. And the nicest one is this OSP12 universality class, which is the zero state Potts model between 2 and 6 dimensions. And it's also related to this hyperbolic space with Grassmann coordinates. And recently I wrote a paper generalizing this to OSP1 to M, which requires higher order interactions of order 2m + 1. And the theory with quintic interactions has upper critical dimension 10/3. So it's epsilon expansion, I think, is a very good approximation for some critical exponents in D = 3. So there is some new kind of 3-dimensional theory that studied. I think that's all.
Okay, let's thank the speaker for a very nice talk.
Yeah, thanks a lot for all the comments and questions.
So if there are more questions, please go ahead and ask.
One perhaps slightly vague question, Igor. For the first set of theories you described, could you imagine that, or do you know whether there is a Vasilyev dual to these theories? Perhaps one in which, when we understand it well, we'll find that there is a sort of bubble instability, a tunneling
exactly.
in ADS.
That was actually, so our motivation, like Simona and I were interested in these Vasilyev theories. And we were wondering, because there is a Vasilyev theory, for example, in ADS6. In principle, it exists. And we just started wondering how to describe the ON model in 5 dimensions. So So then indeed the prediction is that there will be some kind of instanton in Vasiliev theory, which is responsible for these for the metastability of the model. No one has found it yet, but that would be the prediction for this ADS6 Vasiliev theory.
I see. And in 3 dimensions, there are 2 kinds of Vasiliev theories, because there's the free theory, the free field theory, and the Wilson-Fisher. And they differ by slightly different boundary conditions for one of the bulk Vasiliev field.
Yeah, for just the bulk field, but neither one has any instability.
Right. So here you would say something similar in 6 dimensions, that there are 2 kinds of Vasiliev fields. Okay.
Yeah. Okay. Yeah. Again, there will be a free theory which is stable, but then the theory with the other boundary conditions should have some kind of instanton in the bulk.
Right. And since people don't have an action for Vasiliev theory, that's even in principle hard to check, I suppose.
Right. Okay. Yeah, now there are a lot of people are sort of we're arguing about, there are some apparently questions about Vasiliev theory, how to define certain calculations. Even in ADS4, I think people were running into some infinities.
Okay.
But if you just start with the ON model and try to holographically reconstruct that, of course, is fine.
Right.
And recently, so Ofer, Aroni, and Chichester, and the student, I think, wrote some nice papers on doing just that. So one can wonder if you do something similar in 5 dimensions, if that would have some kind of indeed instability.
Right. Thank you.
So Igor, so one kind of tangential question. So I mean, if one goes even higher dimensions and considers, if one wants to understand what happens to the usual theory in higher than 6 dimensions, as you say, one could start with 8 minus epsilon dimension with a.
Yeah, that's actually been done. I mean, so here is basically what happens, that the sigma field, this extra field, it now has not just the usual 2 derivative action, but it has 4 derivative kinetic term. Yeah, so if you write box sigma quadratic term, then everything is fine up to 8 dimensions. You can again develop 8 minus epsilon extensions.
I see.
So in this Gracie paper we also worked on this to some extent. That allows you to go above 6 dimensions. But then, because this higher derivative sigma term, it's sort of manifestly non-unitary, although even at large n.
Okay, yeah, that's
because the sigma dimension will violate unitarity bound.
I see. And also in this last point here, OSP 1/4, the critical dimension is 10/3, and there the in 3 dimensions it became very close to the free theory, right? Because it was
right.
So could it not just be the free theory? Or?
No, I think we know it cannot be strictly free because there are still interactions, but we see the anomalous dimension, but it just has a small coefficient.
I see.
Yeah, I think we clearly see the anomalous dimension. So it's an example of a deviation from free theory by a tiny bit.
And this is a unitary theory, right?
No, this is non-unitary. This is not. Yeah, it's stable, but non-unitary. I mean, this zero-state Potts model is another example. Like, say, in 5 dimensions, people simulated on a lattice using this. But it certainly violates the. Yeah, if you look at the scaling dimensions, like this, let me just show again. So in 5 dimensions, the free dimension will be 1.5, and this is below it, like 1.46. in d equal 4, it's 1, and this is below it. So it's always below the parity boundary. But the rigorous people they're not bothered by this at all in this relation.
And is there a sigma model type action for this also? With
Well, so for OSP 1.2, there is this well-known sigma model.
Yeah.
This one, and OSP 1.4 is analogous. Yeah, you can just write down.
Okay.
All you do is you just solve. You have more pairs of thetas, and you have the constraint.
Yeah.
Yeah, so again, you solve it. So these sigma models are defined for all. So you would get H04, H06, and so on. They're all presumably rigorously defined.
But the way after taking M to 2, you kind of went to 10/3 was the upper critical dimension, right? So that would go down and down and down. Does it always stay up?
Yeah. So what happens is that for OSP 1.6, the upper critical dimension is already below 3. So there is no like nice integer dimension where this
but always above 2.
Yeah, it's always above 2.
Yeah.
Yeah, you just get squeezed between 2 and 3, and not much interesting is happening.
Okay.
But I think OSP 1.4 looks, at least it looks amusing.
Yeah.
Yeah, I don't think people ever notice.
But there do you think there would be a way to impose non-unitarity in some controlled way, in some bootstrap type approach?
Well, there is this Liozzi approach. You got some results from. Yeah, I guess one question is if using that approach one can study this OSP 1.2 theory, for which certainly a lot is known about it.
Okay, thank you.
Are there other questions? Okay. If not, then let's thank Igor again.
Yeah, thanks a lot. Yeah, that was a fun way to start the year.
Thank you so much for taking the time to do this, Igor.
Yeah, no. Hope to see you in person when all this mess settles down.
Yes, I very much hope that as well.
Yeah. Okay, Happy New Year again.
Happy New Year.
Happy New Year. Yeah. Okay.
Bye.
Bye.